So far you've seen the basic operations of a batch system from a user perspective, as well as the operational concerns from a system perspective, and I'm sure that you're excited to go out and run a whole lot of batch jobs. But before you go out and run a million jobs on your local batch system, there's some best practices that you should follow in order to have a productive experience. Now the first thing is, please be careful. You have to think of a distributed batch system as an amplifier that's going to amplify whatever you put into it, and it's going to amplify it by 1,000,000 times. So if you take something good and productive and put it into that batch system, it's going to give you 1,000,000 times of that good and productive thing. But if you take a job that's failing or there's something else wrong with it, the batch system will be happy to amplify that 1,000,000 times, and as a result you're going to have failures and wasted resources and possibly angry system administrators to deal with. So we have to think about some ways that we can be successful before scaling up to 1,000,000 times. Now my first piece of advice is to get organized. In particular, to get organized in how you manage your data in your file system. So if you're going to do a whole lot of runs, make sure you break your work into some discrete units, each corresponding to a file, and then create some kind of directory structure that corresponds to the work that you're trying to do. So in this example here, suppose that I want to simulate 2 different molecules at a variety of different temperatures with 2 different methods. Well, the first thing I would do before getting involved in any kind of batch system is to make a nice structure that has method A at the top and molecule 1 and 2 and then finally the temperatures, so that I can browse this directory structure and see what's been done and how everything is set up. Keep in mind you don't have to do this manually. Write a script or something that's going to generate all of it for you. In fact, you would do well to be able to regenerate it automatically multiple times. Because if you can clean it all up very easily and then recreate it very easily, whenever you have a problem, it'll be a whole lot easier to start over and get things right. Now, as you're planning out your code in your programs, you should make your input and output explicit and discrete. And here's what I mean by that. What you don't want is a program that's going to read and write file names that are hard-coded into its program. So here's an example of a program, a simulation that has hard-coded in. It's going to read models 1, 2, and 3 and produce outputs 1, 2, and 3. Now this may be okay when you're working on one system, but it's going to be very hard to scale up because as you're running thousands of programs simultaneously, they all may be trying to read and write the same files. Furthermore, it's also a problem because we're trying to do 3 different things in one program here. And because it's all in one program, it's going to be difficult to separate those things to run on different machines. So if you have some code that writes fixed file names, please don't do that. Go change your code so instead it takes those file names on the command line. Next thing that you shouldn't do. Do not have a program that reads and writes from the same file. Now again, this might be easy and convenient when you're running on just your laptop, but it's going to make it very difficult to scale up, because if you have multiple programs running simultaneously, one may be accidentally reading the output of the other because you can't control exactly when they run. So don't have a program that reads and writes the same file. Instead, separate your input and output into separate files. So the right model is this. Design your program so that it reads only from certain files, writes only to certain files, and furthermore, the names of those files are given on the command line so that you can change them as you need, and this will allow us to structure your program more easily from the outside. So if you have code like this, go fix it now. It's going to make your life a lot easier as we go forward. Now, another thing you have to worry about is dependencies. So when you write a piece of program on your laptop, you may depend on all sorts of different libraries and services, whether they're Python or Perl or dynamic libraries. And when you get to some cluster that has a bunch of execution machines, they may not have exactly the same software installed. So how do we deal with this? Well, the easiest thing to do in terms of dependencies is to write your program in a compiled language, compile everything together, and produce one statically linked executable. That's the most convenient for distributed computing, because then you have one discrete object which is completely self-contained, which you can move from one node to the other. Now, I understand that's not always possible, and there are good reasons to write in dynamic languages that depend on external objects. But this does make it harder to move your application around. So if you have a job that has a combination of languages and libraries and scripts, you're going to have to think a little bit about what those dependencies are. So let's suppose for a moment that you have a Python program that depends on a bunch of libraries. Well, what you should do is think about it a little bit and look at your code and say, now what libraries do I really depend on here? In this example, you can look at the code and say, oh, this imports library A and library B. Now, where do those come from? Well, they're installed somewhere on your machine that you're working on, and they have to be loaded at runtime. But fortunately, the location of those libraries is usually controlled by some environment variables or other controls. So this could be your Python path or your Perl 5 lib or your LD library path. So what you need to do to get control of your program is to understand the dependencies that you have, not necessarily all the libraries that are out there, but the dependencies you are actually using them, and copy them over into what I'll call a dependency package. Now, that's a fancy name for a directory with a bunch of stuff that I need. So figure out the things that you need, put them in a directory, and then set your environment variables to point to that directory. Now you're in a much better place because you have a nice little package that contains everything that you need. And now when you want to execute somewhere else, you can take everything with you, and your program will run when it moves to other machines. The next best practice I'm going to tell you about is factoring out common actions. So imagine for a moment that you have a simulation, and you've done the work to separate out your input and output files, so you have one input and one output. Good job. But your simulation does one more thing. At runtime, it goes out and connects to a web server and downloads some calibration data. Maybe you want to make sure you always have the most common calibration data. Now, there's nothing inherently wrong with doing this, but think for a moment about what's going to happen if you run a large number of these applications. They'll all read from their own input and output files, and so that's good. But at runtime, they're all going to attempt to download the same file from the same web server. Now, if you have 1,000 programs all start simultaneously and go download this file from one server, you've got a problem on several levels. So the first is, if this is some poor server out on the internet, number one, they may not be prepared to handle 1,000 simultaneous connections. You may very well go crash the service and ruin it for everybody else who's depending on it. And from the perspective of the person operating that service, they're going to see this as a denial of service attack, and they may try to block your network address or call up your university and say some nasty things, and you don't want to get involved in that. But even if that's not a problem, maybe even it's a big scalable public service, even if they can handle the load, it's a bad thing for you. Because if you're trying to download 1,000 copies of that same file simultaneously, well, guess what? All of those downloads have to share the same bandwidth, and so it's all going to run 1,000 times slower, which is a waste because you're all downloading the same file simultaneously anyhow. So this is a bad approach. Don't do that. What you should do instead is factor this out of your code and do it externally from your program. So before you're going to run a large number of simulations, go ahead and download that calibration data so you have one local copy of it on your cluster. And then you take that file and then you feed it to your 1,000 simulations, which all run their computation and produce their output. And that way you're doing the external action once and doing all the internal efficient actions many times. The next best practice is to think carefully about your job lengths. So let's suppose that what you want to do here is analyze 1 million documents using a piece of code such that each analysis is going to take about 5 seconds. This sounds like a good task to send to a cluster. However, if you do it the obvious way, it's not going to work very well. So the obvious way, which is a bad idea, would be to analyze one document in each batch job that you're going to run. Why is this a bad idea? Remember from the last lecture we had this 30-second rule. As a rule of thumb, it takes about 30 seconds just to start one job before it can start running, simply because the batch system has a lot of work to do in order to get the job scheduled and started. So I've got a little diagram which shows you what's going to happen here. If I have 1 million jobs that each take 5 seconds, then first we have to wait 30 seconds for that job to get set up. It computes for 5 seconds and then it's done. Then we want to run another job, and that takes 30 seconds to start up and then 5 seconds and it's done. And we keep on going like this, and you'll see that we're spending most of our time waiting and not actually doing computing. And of course, if I'm doing this on a large number of machines, then I'm wasting a whole lot of machines that other people could be using. So what we need to do here is to run more tasks per job. So we're going to try this a different way. Let's analyze 100 documents in each batch job. So your batch job says analyze this and this and this and this and this and this. Let's do 100 of them. And that way each job is going to take about 8 minutes. All right, so now what happens? We pay our 30-second price, and we run job, and then another job, and then another job, and we keep going out to 100. In this way, we pay the 30-second rule once, but then we execute a large number of jobs. And then if we have lots of machines doing this simultaneously, then we can fill up the cluster with a very large amount of work. My final piece of advice is to scale up by degrees. So it's a common engineering observation that every order of magnitude brings a new problem. So if you want to get up to 1 million jobs, the way to do it is to first run one job, run it to completion, make sure everything goes through the system, get your output, and make sure that output makes sense. Once you're satisfied that that works, then run 10 jobs. Run them all the way to completion, get your output, make sure that it works, and then do 100 and then 1,000 until you get to the scale that you want to do. The reason why things may operate differently at different scales is as you get bigger, you're going to exercise different parts of the system. So as you're growing up to 1 million jobs, you may run into limitations in the performance of the queuing system. You may run into limitations of the performance of the network. You could run into the correctness of your code when you run it with different parameters, because you've never run it so many times before, you never encountered those bugs. And furthermore, you're going to make friends with the system administrators, because they want to understand what people are doing and adjust the system behavior to the actual load. All right, so now you know some of the tricks of the trade for computing effectively at very large scale. And now you're ready to write some large workloads of your own, so go ahead and do the first tutorial on using a distributed batch system.